get together of integrals. In this video, we are going to solve these four integrals. These two are somehow same because there's a plus sign, and these two are somehow same because there's minus sign. Now also, the limits of these two are from 0 to infinity, and limits of these two are from 0 to 1. Now let's begin. Okay, so let's begin with this problem because this is somewhat easier. In the first approach we make in all of these problems is to make a substitution of y equals to ln x. So that will be done in all of the problems. If we substitute y equals to ln x, the integral will go from minus infinity to plus infinity. This will be y square by 1 minus, now x is e to the power y, so e to the power 2y, and dx is e to the power y dy. Yeah. And now the next thing will be integral from minus infinity to infinity. We can divide by e to the power y in denominator. That gives us y square by e to the power minus y minus e to the power y dy. Now there is something special about this function. Now regarding this function, there is something special. So this is from minus infinity to infinity of y square by e to the power minus y minus e to the power y dy. Now let this be f of y. Yeah. And if you try to find out f of minus y, this will be y square by e to the power y minus e to the power minus y, which is just minus f of y. So that's why this function is an odd function. And integral in symmetric domain from minus a to a for an odd function is always 0. So that's why this integral is actually equals to 0. So we solve the first integral, and this is 0. Now let's go to next integral. For this, if you are familiar with digamma function, you might see the solution at hand itself. So this integral, first of all, let's try to do the same as we did earlier. First of all, we can let y equals to ln x, and then e to the power y equals to x, e to the power y dy equals to dx. That gives us integral from minus infinity to 0 of y square 1 minus this is e to the power 2y times dx is e to the power y dy. Yeah. And now, okay, so this one is going from minus infinity to 0. So note that this will again be an odd function, but we don't have a symmetric domain over here. So this approach will not really work in this problem because the domain is just in one side. So that's why we have to think of some other approach. And other approach is from digamma function, and for that it should be in the forms of something like this: x to the power n ln x by 1 minus x and some power of ln x m. If our integral is in this form, we will be able to use digamma function. Yeah. So first of all, let's try to take this integral in this form, and I will show you how we can use digamma function then. Yeah. Now first of all, let's substitute y equals to x square. That gives us y to the power 1 by 2 equals to x, and then y by 1 by 2, y to the power minus 1 by 2 dy as dx. Yeah. And then okay, and then what we can do, we can make this change in limits, integral from 0 to 1, and that will be ln square of y to the power 1 by 2. 1 by 2 comes out and gets squared, so 1 by 4 ln square y by 1 minus y, and then over here 1 by 2 y to the power minus 1 by 2 dy. Now 1 by 8 can be taken out, integral from 0 to 1 ln square y to the power minus 1 by 2 by 1 minus y dy. Now it's in the form that I mentioned earlier. Yeah, and so now we can use digamma function, and let's see how. I will share here. Let's see how. So basically digamma of x, not x plus 1, digamma of x plus 1, or let's say n plus 1 or g plus 1, because x is already used. G plus 1 is negative of Euler-Mascheroni constant plus integral from 0 to 1 of 1 minus x to the power g by 1 minus x dx. So this is the definition of digamma function. Now if we differentiate this with respect to g, this is a constant, so goes to 0, and over here, so 1 by 1 minus x is a constant, goes to 0, and for minus x to the power z by 1 minus x, we have minus x to the power z times ln of x by 1 minus x dx. Yeah, now we already have ln x, but we need ln square x. Yeah, so again let's differentiate again. So double derivative of digamma function, integral from 0 to 1, again minus x to the power z times ln x will be there, so there are 2 ln x, which makes it ln square x by 1 minus x dx. Now minus can be taken to other side, so negative of digamma double derivative of g plus 1 is actually equals to integral from 0 to 1 x to the power g ln square x by 1 minus x dx. So this is the integral formula that we require to solve this problem. So basically over here we have g as minus 1 by 2 and then ln square y by 1 minus y dy. So this will be 1 by 8 times minus double derivative of digamma minus 1 by 2 plus 1. So this is minus 1 by 8 double derivative of digamma of 1 by 2. Now you can find this value from some calculators like Wolfram Alpha, which I've already done, and you see this is actually equals to minus 14 times a Paris constant zeta of 3. So that's why this is minus 1 by 8. Yeah. The mouse pointer. Okay. Wait a second. Just a second. Okay, fine. Now this is minus 1 by 8 times minus 14 times zeta of 3. So that gives us 7 by 4 zeta of 3 as the answer. So this is 7 by 4 zeta of 3. Yeah. Now let's go to next integral. So we have done these two integrals. So this is 7 by 4 zeta of 3. Yeah. And this integral was basically solved using the digamma function. Yeah. Now let's go to this integral. So this was one of the harder integral in this set. Others are somehow easier. So we have integral from 0 to 1 of ln square x by 1 plus x square dx. Now the first thing is, as usual, this will be integral from minus infinity to 0 y square 1 plus e to the power 2y. This is e to the power y dy. Yeah. After this, now what can we do after this? Okay, so again, this will not be an OR function or something like that that we did previously. Now we have to use some other approach. So for this one, we can actually change this. Okay, so first of all, we can also notice something different. So this is actually an even function, yeah. y square by e to the power minus y plus e to the power y. You can see that it's an even function. So for even function, if it's going from minus a to 0 of some even function, this will also be equals to, we can just change this to other domain from 0 to a. We can do that. Yeah, because this is if it's even function, it's something like this. So this area and this area are equal. It's from 0 to a, and this is from minus a to 0. So we can actually make it integral from 0 to infinity. Y square by e to the power minus y plus e to the power y dy. After this, we can try to find the series expansion for 1 by e to the power minus y plus e to the power y. How? We can actually take it to the form of geometric series. If we just divide by e to the power minus y in numerator and denominator, we will have 1 plus e to the power minus 2y dy. So now this is a geometric series with our first term as e to the power minus y and ratio as minus e to the power minus 2y. And for numbers going from 0 to infinity, e to the power minus t, the modulus of this is always less than 1. So this is an infinite geometric series with common ratio less than 1. So we can use that fact, and we will have sum going from r equals to 0 to infinity, e to the power minus y minus e to the power minus 2y to the power r dy. Now let's interchange the sum and integral. Sum from 0 to infinity, integral from 0 to infinity. Is it? Yeah, it's. And we have y square. This is minus 1 to the power r and e to the power minus y times 2r plus 1 dy. Yeah. Now you might probably see some sorts of gamma function over here. Yeah. We have minus 1 to the power r outside, and then integral from 0 to infinity of e to the power minus 2r plus 1 times y square dy. Let's say this is also Laplace transform instead of gamma function, and so this over here is s. Yeah, so we know it's Laplace transform, so we will use that. Sum from r equals to 0 to infinity of minus 1 to the power r. This will be gamma of 3 by 2r plus 1 to the power 3. So basically, if we had n over here, it would be gamma n by s to the power n. So I did that. Okay, so now after this, am I missing something? It feels like I'm missing a 2 over here. Let me just check once. Yeah. So first of all, it was that. No, I'm not missing anything. Fine. Okay, so now this is 2 times sum from r equals to 0 to infinity minus 1 to the power r by 2r plus 1 cube. So we have this sum. Now you might know the definition of Dirichlet beta function, which is sum from r equals to 0 to infinity of minus 1 to the power r by 2r plus 1 to the power s. This is Dirichlet beta function. Now over here, this is just Dirichlet beta of 3. 2 times Dirichlet beta of 3. Now we can again use calculators to find beta of 3, because these are standard values and there are some standard ways to find these values. So that's why for this function as well and some for others, these are some standard values. So that's why I'm going to use calculators, because there are already some obvious or well-known ways to find those values. Dirichlet beta of 3 is pi cube by 32. So this is 2 times pi cube by 32. So this is pi cube by 16, and that's the answer. So we solve this problem as well. This is pi cube by 16. And the answers are pretty nice, you know. This is in terms of zeta, and this is in terms of pi. Pi cube by 16. Now you might notice here something. Yeah, this integral, I will see it in the fourth one itself. Let me not be so excited. Okay, so this integral over here can be written as the sum of two integrals. Yeah, x square dx and integral from 1 to infinity. And you can find out that these two integrals are actually equal. So let me show you that this is actually equals to this integral. Yeah. So if we substitute y as 1 by x, you get integral from 1 to 0 of ln square 1 by y, that is minus ln y whole square. So this is again ln square y itself. And over here, you will have y square plus 1 times y square. And then dx will be minus 1 by y square dy. Y square cancels out, and minus 1 changes the integral from 0 to 1 again. Ln square 1 by y square plus 1 dy. So you see, this integral is actually equals to this, and this one is same as this integral. So these two are all actually equal. So that's why the sum of these two will be integral from 0 to 1, twice of the integral from 0 to 1, ln square x by 1 plus x square dx. Now we have already solved this integral. Yeah. And the answer was pi cube by 16. So this is 2 times pi cube by 16. So the answer is pi cube by 8. So we solved this integral as well. So all of the integrals are now solved. This is pi cube by 8. Hope you enjoyed the integral. This involved odd function. This involved digamma function. And this involved just the sum integral exchange in geometric series. And this involved this function, like just the u substitution as 1 by x helped us solve it, and also we had to break the integral. That's how we solve all of these integrals. Hope you enjoyed the video. Thanks for watching. Do like, share, subscribe, and look forward to seeing you in the next video.